We'll proceed on estimating a critical point if whether it is maxima or minima. So that is the concept that we are pursuing. So if I have a function, if I have a function and somehow the function is differentiable, it's a continuous function and it is differentiable, and at few points the function is has extreme points or critical point. Extreme point in a sense that the function is like sine wave. When it is sine wave, then at some points it is kind of there is a slope in one direction and again slope in another direction. Then those points are called maxima minima points. Means this is what kind of we are seeing. So this is the concept that we want to kind of pursue. Okay, so nice it is that if I have an extreme point, so kind of in detail we have talked about what is extreme point. So if I have extreme point in the function, then those extreme points there the differentiation is zero, means there is no slope. So if I have a function like this, then at this point, if I see this differentiation, if I see the derivative in this side, then it is positive. If I see derivative along this side, then it is negative. Derivative means what is if I change one unit along the independent variable x-axis, how many unit of change that we see along y-axis. So that is derivative. So if I have a curve like this, then if I go this side, per unit change along x-axis bring positive change along y-axis. But if you go like this, then per unit change along x-axis brings down the vertical. This proves that the dy by dx along this side is positive, where this side it is negative. But if I have a curve like this, there is a point where dy by dx, the slope or rate of change is zero. That is called extreme points. Means these are extreme points. There is no slope. There is no rate of change. So but extreme points can be minimum also. If it is like this, then also there is extreme point like sine wave minus pi by 2, it is minimum, whereas pi by 2 it is maximum. So extreme point can be minimum and extreme point can be maximum through algebraic fundamentals. Through differentiation, can we say that this point is maxima or minimum? That is the concept. Now, first we saw that in 2D, if I do double differentiation, if double differentiation is positive, then it is minima. If it is negative, then it is maxima. But that would not work in 3D, where the two independent variable we have. It means in surface equation. In 2D we have line equation. In 3D we have surface equation. If that is the case, then it would not work because we have two independent variables. Now double derivative means what? If I have two independent variable x and y, then double derivative is fxx, double derivative is fyy, double derivative is fxy also. Which one we are talking, that I have to check. So it is different. But anyway, beyond that, then what we saw, that if I have a parabolic equation, somehow, if I have a parabolic equation, then parabolic equation has a peculiar nature, that it is either minima or maxima. That's it. Only one. Like sine wave has so many minima and maxima, but parabolic equation has only one, either maxima or minima. Y equal to kx square. If k is positive, then it is global minima. If k is negative, then it is global maxima. So if I want to find a portion of a function where we have extreme point, that portion is maxima or minima, then solution what I have is that portion can I remap to a parabolic function. This is something that personally I don't like. Means by force, the way you like, you are molding something. Okay, so certainly it is not preferable, but what we can do means we also have some limitation in life. So if fx equal to kx square, if fx equal to if I have independent variable, there is a function over it, that is fx. So if I have fx and fx is any polynomial function, can I map to another function gx, where gx is parabolic function kx square, or kx square plus y square, or gx equal to x square plus y square? If that is the case, then x square plus y square means along x axis it is x square, along y axis it is y square. Okay, so along x axis it is x square, along y axis it is y square. If I rotate it, then it becomes a paraboloid. Parabola in xz plane, parabola in yz plane, parabola in xz plane, and parabola in yz plane. Then it becomes a parabola. So if I have fxy equal to x square plus y square, then it is parabola in xz plane x square, parabola in yz plane, that is y square. So x square plus y square is is a paraboloid, or fx equal to x square, that is parabola. So if I have either a parabola or if I have a paraboloid, then it has certainly it is either maxima or minima. There can be only one. This is the nature of parabola. So if it is fx equal to x square, then it is minima parabola. If fx equal to minus x square, then it is maxima parabola. Similarly, if fxy equal to x square plus y square, then it is minima parabola. If it is minus and then braces x square plus y square, then it is maxima parabola. So this is what we saw. Now, can I convert any function into parabolic function? Then quickly I can say, I'll see the coefficient, it is positive or negative. Then quickly I can say that at this point either it is maximum or it is minimum. Now, if I have a function fx, if I have a if in two dimensional, if I have a function fx and fx is a polynomial function, so t plus t square plus t to the power 5 plus t to the power 7, like that, plus t to the power n. So that function fx, ft, or fx means x plus x to the power 3 plus x to the power 5 plus x to the power 7 x to the power 11 plus x to the power dot dot x to the power n. If I have polynomial function like this fx, then can I represent it using another function gx, where gx is a line, where gx is a line. So that means we have seen this in detail. Then the equation of any line is y equal to mx, where m is dy by dx. So I can rather say that if I have a line, if I have a line equation, I have a line equation like y equal to 10x. So this is equation of a line, or 10x minus y equal to some constant. Can I reproduce this line using algebraic differentiation, using algebraic derivative? This is what we saw. If I have a line, then can line be reproduced using derivative calculus algebra, derivative algebra? So we saw that y equal to mx, if I write, then I can reproduce it. If I have a polynomial equation fx, that is t to the power 2, then can I represent it as derivative gx? Then I have to do d2y by dt square, or fx equal to x to the power 2, then gx in kind of a derivative, in kind of derivative algebra, then it will be d2y by dx square. So we saw that if I have a kind of a line, and that line if I want to represent using calculus differentiation, then I have to calculate dy by dx, and then I have to go with a line equation y equal to dy by dx into x. If I have a fx that is in x square, then if I want gx in differential calculus, then it will be kind of d2y by dx square, y equal to d2y by dx square into x square by factorial 2. If fx is in x to the power 3, then if I want gx as a differential kind of curve, then dx equal to d3y by dx square into x to the power 3 divided by factorial 3. This is what we have seen. You can refer our last video. So if I have any function, polynomial function in t to the power x to the power n, fx equal to x to the power n, if I want to get exactly same function through calculus, then I will have gx equal to dny by dn square, dny by dx to the power n into x to the power n divided by factorial of n. Now, if I have a polynomial equation fx that is mixture of everything, x to the power 0, x to the power 1, x to the power 2, x to the power 3, up to x to the power n. How I can estimate at this polynomial? If I have fx equal to x to the power 0, x to the power 1, x to the power 3, x to the power 7, x to the power 11 plus and x to the power n, where plus can be converted to minus somewhere and coefficients for each x I am removing. If that is the case, fx is there, then if I want gx in terms of differential calculus algebraic, then gx, if I want as a straight line, I have full function, but I want only as a straight line. Convert this function, polynomial function, up to x to the power n, x to the power 0 plus x to the power 1 plus x to the power 3 plus x to the power 1 as a single line. Then gx equal to dfx by dx, dy by dx at x equal to 0. So at any point, if I have fx and if I do dfx by dx, then I will get another equation that will be function of x only. Now I'll convert it to a scalar, replacing x as x0. If I convert this x as x0, then dy by dx would come as a scalar. Now I have another function gx. I talked about fx, differentiating fx single derivative dy by dx. Whatever scalar value I get at point x equal to x0, now I have another function gx, that is dy by dx into x divided by factorial 1. If that is the case, then dy by dx, whatever I have received at point x equal to x0, that scalar into x divided by factorial 1 is the equation of line that is equivalent to. So gx is equivalent to fx. Certainly it is not possible because fx is a high profile polynomial function. Means x power 0, x power 1 and then x to the power n. It may be complex function, but we are converting fx to gx with single derivative, that is a single line. But they are same at point x0. If I have a complex curve fx and I have gx equal to dfx by dx into x divided by factorial 1, if that line is there, then that line would touch that curve at point x equal to x0, where we have calculated dy by dx, that is a scalar at x equal to x0. So any polynomial I can estimate with a single line. Any polynomial I can estimate with a parabola, means to the power x square, any to the power x3, any to the power xn. This is what I show. If we want to be represented at xn, then d to the power gx equal to d to the power n y by dx power n dny by dxn into x to the power 1, x to the power n divided by factorial n. Okay, so nicely that we have seen. Now any fx, if I have any fx and I want that fx to be represented through differential algebra gx, then either it can be of degree 1 2, 3, 4, 5. Any degree I can represent. But good thing is that whatever they represent, if they represent in x to the power 2 or x to the power 3 or x to the power 1, okay, but they would touch the fx, gx would touch the fx at point x0. So if fx is a curve, gx may also be a curve. If I take t x to the power 3, x to the power 4, x to the 5, those are curves, but they would touch it at x equal to x0. So if I have x to the power n in fx and gx also, if I take x to the power n, then they would be similar. But if fx has so many x terms, then there will be deviation. So we can say that more or less for any fx, I can have a gx equal to fx0, fx0 or y0 also we call it, fx0 plus dy by dx x equal to x0, dy by dx at x equal to x0. So fx0 plus, and then dy by dx x by factorial 1 plus dy by d2y by dx into x square by factorial 2 plus d3y by dx cube into x cube factorial by 3 plus dny by dxn x to the power n by factorial n. If I add everything, then I can say this dx is the kind of approximation of the fx, irrespective of what the fx is. So if fx has maximum power as 10, then gx will go up till 10 only, because beyond that the full differentiation will be 0. Okay, so this is what we have seen, that if I have fx, then estimation of fx through differential equation in algebra, that is gx, is fx at x0, fx at x0 plus dy by dx x by factorial 1. Okay, and then plus d2y by dx square into x square by factorial 2 plus, like that. Now if I am very peculiar that it is passing through a point that is x0 and fx0, then nice that if I replace all x with x minus x0. So if I am representing a curve with another curve, okay, and that curve they touch each other at point x0, they touch each other at point x0, then x0 and fx0 is the x comma y. So x is x0 and y is fx0. So at x0 fx0, then the gx passes through. If that is the case, then new equation for the gx would be fx0, that is y0, plus dy by dx into x minus x0 by factorial 1 plus d2y by dx square x minus x0 whole square by factorial 2, and so dny by dxn x minus x0 to the power n divided by factorial n. So this is the estimation of fxy as gxy as far as estimating any polynomial equation through differential. Okay, but great thing what we saw, that if I take up to power 2 only, then it will become fx0 plus dy by dx x minus x0 by factorial 1 plus d2y by dx square x minus x0 whole square divided by factorial 2. Now any maxima or minima, if I want to see if it is, if any extreme point, if I want to check it is maxima or minima, then those extreme point dy by dx is 0. So fx0 plus next is 0 plus dy by d2y by dx square into x minus x0 whole square by square root. So x minus x0 whole square, I leave it, and d2y by dx square, d2y by dx square by factorial 2. So factorial 2 also I leave it because it is always positive. So I'll just check that d2y by dx square at point x equal to x0 is positive or negative, because we came to a parabolic function. This is what we saw. Now, now this is the kind of line concept. If I have 2D, if I have a line curve fx, then I have gx, and that gx I have calculated up to only second degree, where first degree is anyway 0 because dy by dx is 0. So at extreme point we catch only the second power, and that comes as d2y by dx, that is the coefficient. So if I say that gx is a new function, then if I remove fx0, first is fx0, if I take it out, then it comes as d2y by dx square into x minus x0 whole square by factorial of 2. So now I have that the sign of gx is the sign of the coefficient, that is, so gx is in form of parabola. If it is in form of parabola has a coefficient kx square, y equal to kx square. So if k, that is d2y by dx square divided by factorial 2, if that is the k, then the sign of k decide that extreme point is maxima or minima. If it is positive, then that is minima. If it is negative, then that is maxima. It is exactly what we had earlier seen, that if I do dual derivative, then I have to see the sign. Same thing came with this function also. Now, we started with fx as a line. Now we will do fx as a surface. If fx is a line, now fx is a surface. If fx is a surface, then there are two independent components, x and y. So fxy. So fxy, I'll take a surface equation simple as x plus y. If it is x plus y, then it is a flat surface. If this is xy plane, on xy plane I have points as x comma y. Against each x comma y, I have fxy as vertical. So vertical, if I combine x plus y, then it will be a kind of a surface. Okay, when x is 0, y is 0, then it is 0. When x is 1 and y is 1, then it is 1. When x is 1, y is 0, so it will be a surface. If I have a surface x plus 1, then this surface is a kind of uh, flat surface. If it is a flat surface, then I can represent it as a, if it is fxy equal to x plus y, then gxy, that is a parabolic, that is a straight line. If it is power of 1, then gxy would be a straight line. What is a straight line? So gxy, that is z equal to gxy, then it is dz by dx into x plus dz by dy into y. This is what we have already seen. So the representation of a plane, that is fxy equal to x plus y, as another plane exactly same when we represent it through differentiation and algebra, that is gxy. So gxy equal to dz by dx into x plus dz by dy into y, m1 x plus m2y, or mx plus ny. This is what we saw. So if it is x plus y, then dz by dx is 1, dz by dy is 1. Then z equal to x plus y again. So we can exactly reproduce. If fxy is x plus y to the power whole square, power 2, earlier we were taking x square in 2 dimensions. In 3 dimensions, now it is x plus y whole square. If it is x plus y whole square, then it turns out as x square plus y square plus 2xy. If that is the case, then I have to represent it in gxy. Okay, so scenario is I have to represent in gxy. Now let's go to the 2D. So if in 2D, if I have fx equal to x square, then gx is d2y by dx square into x square by factorial 2. Okay, so this is what we have seen in detail how it is. So now here fxy is x plus y whole square. That is x square plus 2xy plus y square. Now, now there can be three kind of differentiation. One is you differentiate in a way that it will turn up to a scalar. That is the idea. So now if I do d2y by d2z by dx square d2z by dx square. Then whatever remains, so x, y and y square term will go up. Only x square, if I differentiate it with 1 time, then it will become 2x. If I differentiate it again, then it will become 2. X, y and y square will go up. So d2z by dx square, whatever we are getting, then if it is x square, if it is x square, then coefficient we are getting 2, 2 into 1. So now d2z by dy square what we are getting. So that is x square plus xy will go away. Only y square will remain for the differentiation twice. What is dz by dx into dz by dy? This differentiation, because these are the three possible things that I am seeing with a fxy equal to x square plus 2xy plus y square. Idea is that if I have a function fxy equal to x square plus 2xy plus y square, I have to come up with another function gxy, that is algebraic differentiation, and it should be exactly same as fxy. That is the concept. So now I would say that it should be d2z by dx square, d2z by dx square into x square by factorial 2, because it is power 2, plus d2z by dy square into y square by factorial 2, plus dz by dx into dz by dy. Okay, or we can say that fxx into x square. Fxx means d2f by dx square. Fxx means d2f by dx square. Fxx into x square by factorial 2 plus fxy into xy, that's it, by factorial 1 into factorial 1 plus fyy into y square by factorial 2. Why I am saying like this? So now I have fxy equal to x square plus 2xy plus y square. Now if I do fx's d2x by d2z by dx square, fxy is z. So d2z by dx square, I have fxy equal to x square plus 2xy plus y square. That is actually x plus y whole square. Now that is z equal to x square plus 2xy plus y square. dz by d2z by dx square is 2. X square, first it became 2x, then it became 2. What is d2z by dy square? Then again it is 2. The y square became 2y and then 2. What is dz by dx? dz by dx is 2x plus 2y. What is dz by dx into dz by dy? So 2x gone. Now only it remains is 2. Okay. Now can we see that the fxx is 2, fyy is 2, and fxy is 2. Now if we see closely the equation again, x square plus 2xy plus y square. So x square had no coefficient. Okay, x square, just y square, but xy had coefficient at 2. So now if I see fxx, then it is 2. Means whatever the exponent we had, double differentiation came as the scalar value. Same as y square 2. But 2xy there is nothing extra we got. 2 was anyway, it was there. So now if I want to reproduce it, then I would say fxx into x squared by factorial 2, because 2 we got extra, so I'll divide by 2. fxy plus fxy by factorial 1 into factorial 1 means nothing, fxy, because we did not get anything extra, plus fyy into y square divided by factorial 2. So fxx into x square divided by factorial 2 plus fxy into xy plus fyy into y square divided by 2. Okay, what about if I have x plus y to the power 3? X plus y to the power 3. Then it will come as x cube plus y cube plus some x square y plus some xy square plus something, something, something. Okay. Now, if I do d3z by dx square, d3z by dx square, then it will come x cube will become 3 into 2. So first differentiation will get 3x square, then 3 into 2 into x, then 3 into 2. Other will go away in 3 differentiation. So d3z by dx square is factorial of the power. If x is power 3, means 3 factorial. Now if I try to get back gx from fx to gx, then it will be fxxx d3z by dx cube into x cube divided by factorial 3, because factorial 3 extra we are getting. If it was x to the power 3, if fx equal to x to the power 3, then d3fx by dx cube equal to 3 into 2 means 6 I am getting extra. So 6 I have to divide to if I want to reproduce it. So if I have a function fxy equal to x plus y to the power 3, and I want to reproduce that function as gx in terms of differentiation, then it will come as fxxx into x to the power 3 divided by factorial 3 plus fyy into y to the power 3 divided by factorial 3 plus, then if we had kind of 4x square, I don't remember what is x plus y to the power 3, then if we had 4x square y, 4x square y, if I calculate fxxy, this is what I can do there. Fxx 2 times differentiation with x and then y. If that is the case, then if it is power of x is power of 2, then I have to divide here by factorial 2. So I would say fxxy into x square into y divided by factorial 2. Same, the way we are doing, same I have to divide by that factorial. So if it comes as x sum x into y square, if that is the situation, sum x into y square, then it will lead to fxyy dz by dx into dz by dy into dz by dy. If it is sum x plus y square, then here it will come as fxyy into xy square divided by factorial 2. Actually, it should be divided by factorial 1 into factorial 2. Okay, so any polynomial equation in 3 dimensions where two independent components are there, 3 dimension where two independent components are there, x and y. So if I have fxy, if I fxy and two independent components are there, x and y, then so nicely I can fxy, I can convert. Okay, so if I have fxy and fxy is a polynomial function where x is in power of 1, 2, 3, 4 up to n. Okay, then if I want gx, if fx is full, x to the power 1, y to the power 1, x to the power 3, y to the power 3 up to n. If I want gx, then I would start with m1 m1 means fx into x plus fy into y, that is the first dimension, plus fxx into x square by 2 plus fxy x into y plus fyy into y square by 2 plus fxxx into x to the power 3 divided by factorial 3 plus fxxy into x square y divided by factorial 2 plus fxyy x into y square divided by factorial 2. I believe it will be plus fyy into y cube divided by factorial 3 plus then we have to go like this up till n. What is n? I don't know. Certainly in n it will be fxxxxxxxxxxx up till n into x to the power n divided by factorial n. One term, this one will be there. Another will be fyy means d to the power nz by dyn into y to the power n divided by factorial n. These two terms will be there and then addition. So this is how we can grow in polynomial the power value x plus 1, x plus 1, x plus y, then x plus y to the power 2, then x plus y to the power 3, like that x to the plus y to the power n. Okay. Now the idea is, can I convert any fxy to gxy where gxy is parabola? That is the concept. So that I can say that any point is maxima or minima. That is the concept. Now leave everything 3 and beyond. So if I have fxy, and that is polynomial up till x to the power n, y to the power n, but I will represent it as in the power of 1 and 2 1. Whatever gx looks like, it's all right to me because I know that I have to, it would touch fxy and gxy, they will touch each other at point called x0, y0, that is the extreme point. Idea is that if I have a surface, and surface has extreme point, either it is maxima or minima, or we cannot define at some point it is maxima also, it is minima also, like saddle point we saw that in x it is like this and in y it is like this. If that is the case, at that point in x direction it is minima, at y direction it is maxima. That also extreme point we will see. So in 3D where we have surfaces, either it can be minima in both directions, in xz plane also it is minima, and yz plane also it is minima, like fxy equal to x square plus y square. If fxy equal to x square plus y square, then it is a paraboloid where it is minima in both directions. So there is a single minima. If fx equal to minus and in bracket x square plus y square, if this is a paraboloid, then it is upside down. Okay, now this is the, if this was paraboloid, then this is the paraboloid. Minus x square minus and then in bracket x square plus y square. If that is the case, then it is a paraboloid which has one maxima, global maxima. But if I have a saddle point in x direction, it is like this, xz plane, where in yz plane it is like this. So one is like this and one is like this. Just think about the condition. Okay, so one side it is like this and one side it is like this. So it's a saddle on horse. So at that critical point, in one direction it is maxima, in the other direction it is minima. We don't know what it is. Or it can be like a cone. If I have a cone, then at cone point, then the dy by dz by dx or dz by dy is undefined. So that also we'll see. Now anyway, if I have a fx, any fx, can I convert it to a paraboloid? If I have a fx, can I convert it to paraboloid? If I have paraboloid, then looking at the coefficient of paraboloid, quickly I can say that x0, y0, that is the extreme point, it is maxima it is minima, or it is maxima or minima both, or we don't know, like cone case, we don't know, or maxima or minima both, like saddle point, or it is maxima or minima. So convert fx to gx where gx is paraboloid. How we can do? Now we the way we in 2D the fx and gx we converted, same way we'll do in 3D. So now fxy here, fxy convert, I have to convert it to gxy. So now we will do mx plus ny, or m1x plus m2y, or dz by dx at point x equal to 0 plus dz by dy at point y equal to y0. One is x equal to x0, one is y equal to y0. Because I know that extreme point is at x0, y0. If extreme point is at x0, y0, then it will become like z equal to, or gxy, not the fxy, gxy, the converted algebraic differentiable function gxy equal to dz by dx into x plus dz by dy into y. This is the single dimensional monomial plus then by means binomial. So d2z by dx square into x square divided by factorial of 2 plus dz by dx into dz by dy plus d2z by dy square into y square divided by factorial of 2. Okay, so this is what it is. Now if I go in full term, so full term, the equation of any plane in 3D is z minus z0 equal to dz by dx into x minus x0 plus dz by dy into y minus y0, where dz by dx is scalar, and when dz by dx was made, it may come as a algebraic equation where x we have to replace with x0. Okay, so dz by dx is a scalar where x I have to replace with the x0. Okay, and dz by dy is a scalar where y I have to replace with y. Okay, if dz by dx is in y also, then replace with the x0 y. So now I have gxy equal to f x0 y0, z minus z0 equal to dz by dx into x minus x0 in braces plus dz by dy braces y minus y0. This is the normal equation of a surface where the surface is passing through a point that is x0, y0, z0. If that is the case, then equation of surface is z minus z0 equal to dz by dx x minus x0 plus dz by dy y minus y0. Now if the surface is passing through the origin, then z0, x0, y0 all become 0, and it becomes z equal to dz by dx into x minus x0 dz by dx into x plus dz by dy into y, because x0, y0, z0 is 0. But if it is passing through a valid non-zero x0, y0, z0, then it becomes z minus z0. Now z0 I can take out that side. So z equal to z0 plus dy dz by dx into x minus x0 plus dz by dy into y minus y0. So z0 is nothing but f x0 y0. Whatever the f is at x0 y0, that is z0. Now the gx, the new function that we are estimating from the fxy. So from fxy we are estimating a new function that is gxy, and I am hopeful that it will be paraboloid. So gxy equal to f x0 y0 plus dz by dx into x minus x0 plus dz by dy into y minus y0 plus d2y by dx square x minus x0 whole square by factorial of 2 plus dz by dx into dz by dy x minus x0 into y minus y0 by factorial of 1 into factorial of 1 plus d2z by dy square y minus y0 whole square divided by factorial of 2. Okay, I would repeat it. So gxy equal to f x0 y0 plus dz by dx x minus x0 plus dz by dy y minus y0 one dimension over plus d2z by dx square x minus x0 whole square by factorial of 2 plus dz by dx into dz by dy into x minus x0 y minus y0 divided by factorial of 1 plus d2z by dy square into y minus y0 whole square divided by factorial of 2. Okay, now we have extreme point in fx at point x0, y0. This is what we have seen. Now I have to find this extreme point is maxima or minima. Now in this equation, fx0, y0, okay, just leave it, take it out, considering it is passing through the origin. Now we have another term that is dz by dx and dz by dy. So dz by dx and dz by dy are 0 because that is the extreme point. When there is extreme point, the first derivative is 0. So dz by dx and dz by dy are 0. So first all term, 3 terms gone. Now I have gxy equal to d2z by dx square x minus x0 whole square divided by 2 or factorial of 2 plus dz by dx into dz by dy into x minus x0 into y minus y0 factorial of 1 plus d2z by dy square y minus y0 whole square divided by factorial of 2. So only 3 terms comes into the picture, or I can say fxx. Okay, now we have considered it is passing through the origin. Just leave it x0 and y0. fxx into x square divided by 2 or fxx by 2 into x square plus fxy into xy plus fyy by 2 into y square is fxx by 2 into x square plus fxy into xy plus fyy by 2 into y square. This is a typical scenario of an equation that is ax square plus bxy plus cy square. Same, right? Where a is fxx by 2 and c is fyy by 2 and b is fxy. So I have gxy equal to fxx by 2 into x square plus fxy into xy plus fyy by 2 into y square. If I have algebraic equation that is ax square plus bxy plus cx square, one imaginary algebraic equation, then it maps a as fxx by 2 and c as fyy by 2 and b as fxy. Now, idea is, can I convert this ax square plus bxy plus cy square as paraboloid? Because at the end, gxy should be paraboloid. If gxy is paraboloid, means it has to be in form of k into bracket x square plus y square. K can be positive, k can be negative scale. If k is positive, then paraboloid is global minima parabola. If k is negative, then paraboloid is global maxima parabola. Ax square plus bxy plus y square I have to push in a form of k in bracket x square plus y. Can I do something like this? I can take it out. Ax square plus bxy plus cy square. If I take it out a and then inside it would remain at x square plus b by a xy plus c by a y square. That will remain inside. If I take a out, just take a out and inside the bracket we have x square plus b by a xy plus c by a by square. Now that this term I can represent as x plus b by 2a y, x plus b by 2a y whole square, x plus b by 2a y bracket close whole square plus in another braces c by a minus b square by 4a square bracket close y square. So net ax square plus bxy plus cy square, that I can represent as a and then full bracket. A is completely outside, then full bracket. Inside full bracket, I have two braces plus one braces plus another braces. So first brace is x plus b by 2ay whole square. Another brace is c by a minus b square by 4a square. Braces close and then y square. If I break it, then it first will come as x square plus b square by 4a square y square plus then 2 2b 4 a square b 2 x plus b by 2a y whole square. So x square plus b square by 4a y square plus 2 2b by 2a. So b by 2 plus, okay, plus 2b by 2a, okay, xy. So b by a xy. Now that side c by a minus b square by 4a square and in braces y square. So c by a y square minus b square by 4a square b square. So first braces we had b square by 4a square y square, that will go away. So the remaining part is x square plus b by a xy plus c by a y square, that will remain. So now a is completely outside that I had kept. Now if I mix it here, then it becomes ax square plus b by a y square, then c by a y square, then that will become cy square. And then we have another term in xy, that will become bxy. Okay, so it will come back to ax square plus bxy plus cy square. Now can we see this? A outside and inside that big bracket, and then first braces is x plus b by 2a, x plus b by 2ay whole square. So first term is whole square, that equivalent to parabolic equation that we are saying z equal to x square plus y square. This is parabolic equation, z equal to x square plus y square. Here I have z equal to a, and in big braces, the first term is inside braces is x plus b by 2ay whole square. So first whole square came plus in other braces c by a minus b square by 4a square braces close y square. So first x square, next y square. So it came as a parabola. A and then big braces, inside that I have two braces. This is what is expected, right? The parabolic equation in 3D where z equal to k and in braces x square plus y square. K x square plus y square. If k is positive, then it is negative, it is minima paraboloid. If k is negative, then it is maxima paraboloid. Here a came out. So a is k. Now inside big braces I have two squares. The way there also k and in braces x square plus y square. Here a outside and inside that I have two square. One square is x plus b by 2a y whole square. So this is always positive. That is equivalent to x square there. Plus another one is c by a minus b square by 4a square bracket close y square. So that y square has this as coefficient, that is c by a. minus 4 minus b square by 4 square. If I resolve it, then it will become 4ca minus b square divided by 4a square. C by a minus b square by 4a square, that will be resolved to 4ca by 4 4ca minus b square by 4a square. So it will resolve to a, and then big braces. The first, inside that there are two braces. The first brace is x plus b by 2a y whole square plus 4ca minus b square divided by 4a square into y square. Now, if 4a square, the denominator is always positive. So the y square, the coefficient remains is 4ac minus b square. If 4ac minus b square is positive, then we come as a paraboloid as f gxy equal to k x square plus y. Gx equal to k x square plus y square. If that is the case, then gx is a paraboloid. If that is the case, if gx is a paraboloid, then k braces x square plus y square, then depend upon the k, I have, it is a minima paraboloid or maxima paraboloid. Now here gxy equal to a, and inside that braces there are two squares. One is x plus b by 2ay whole square. So we are not worrying about it because it is always positive. Plus b square plus 4ac minus b square divided by 4a square y square. So here the y square can be negative, means it will come as a term. If I take the paraboloid equation, then we had come gx equal to k x square plus y square. But here in real life, it can be x square minus y square. It can be x square plus y square. It can be x square minus y square. So I have now gx equal to a, and inside the bracket x plus b by 2a y whole square, that is first x square, plus 4ac minus b square by 4a square y square. This 4ac minus b square can be positive, can be negative. If it is positive, then we come as a term as gxy equal to k x square plus y square. Now a is outside here, k is a. So if inside that, if it is in term of x square plus y square, then depending upon a, it is maxima paraboloid or minima, where a is fxx by 2, c is fyy by 2, and then b is fxy. Okay. Now, if 4ac minus b squared comes negative somehow, then it will come as the general equation will come as a, and then x plus 2 x plus a by x plus b by 2a y whole square. So first term is whole square plus negative some negative y square. Okay, if 4ac minus b square is positive, then it will come as a, and inside braces first term is square plus positive, first term is x plus y square. So whatever, x square plus positive y square. So it is a parabola. But if 4ac minus b square is negative, then it will come as a, and inside braces x square minus y square. If it is x square, if I have equation gxy equal to k x square minus y square, then in xz plane it is a parabola. In xz plane it is a parabola. In yz plane it is also a parabola, but upside down. This is a saddle point. Now, if 4ac minus b square is positive, then it is a complete parabola. Now, depending upon the value of a, that is outside cap, I can say it is a minima paraboloid or maxima paraboloid. But if 4ac minus b square is negative, then it will come in a term where gxy equal to k inside bracket x square minus y square. So one side it is a minima paraboloid, and other side it is maximum paraboloid. XZ plane is minimum paraboloid and XY plane is maximum. So it is a saddle point. It is neither a maxima nor a minima. No need to go for a value at all. If 4ac minus b square is negative, then it is neither maxima nor minima. Okay. Now, what about 4ac minus b square is 0? If it is 0, then I have only first term, that is a, and then inside braces we have x plus b by 2a y to the power whole square. So whatever it comes, it is a paraboloid again. Whatever it comes, it would be like this. So when d equal to 0, then we can say that we don't know. It can be either maxima or it can be minima or it is undefined. Now everything depends upon the second one. Now we came to gx equal to a, and inside braces x plus b by 2a y whole square plus b plus 4ac minus b square by 4a square y square. Depending upon 4ac minus b square, if it is positive, then it is a paraboloid. If it is negative, then it is a saddle point. If it is 0, then it can be anything. Either it is maxima or minima. So if it is positive, then it can be a minimum, it is a minima for a paraboloid or maxima paraboloid. If b 4ac minus b square is negative, then it is a saddle point. So it is neither maxima nor minima. If it is 0, then only first term exists, and that is x plus b by 2a y whole square. So a into x plus b by 2a y whole square. So it is like a paraboloid shape only, but we don't know what it is. It can be maxima. So then we have to calculate through the kind of contour line. Okay, so nice it is. So we'll work out on this. We'll take examples, few examples, and we'll work on it. So now, if I have a function fxy, I convert it to another function gxy, and gxy is a polynomial function, differential algebraic, where maximum power is 2, and first power 1, anyway it becomes 0 because at point x0, y0, first derivative is 0. So everything becomes 0, and it came as fxxy2 into x square plus fxy xy plus fxx x f fxx by 2 into x whole square plus fxy into xy plus fyy by 2 into y square. This resembles the algebraic equation ax square plus bxy plus cy square. That again resembles where I have to keep outside, and then I have two squares inside it. One is x plus b by 2a y whole square, and another is 4ac minus b square divided by 4a square into y square. So there are two square that we saw in dxy. If dxy equal to k x square plus y square, then it is a full-fledged paraboloid. Depending upon the value of k, we decide that it is a minimum paraboloid or maximum paraboloid. But if it is k x square minus y square, then it is a saddle, and we say that it is neither maxima nor minima. This is what we saw. Now k is replaced by a, and x square plus y square. So x square is very nice, that is x plus b by 2a y whole square. But y square has coefficient, that is 4ac minus b square. If 4ac minus b square is positive, then we are exactly paraboloid. Now depending upon the outside a, I can say it is a minima paraboloid or maxima paraboloid. So if it is a minima paraboloid, then x0, y0 point, x0, y0, z0, whatever the surface is, that is minima, that extreme point is minima. If it is a maxima paraboloid, then x0, y0, z0 as a surface, that is a maxima paraboloid. Now the y square coefficient 4ac minus b square, if it is negative, then it turns out to be a saddle point. So full is neither maxima that point what we are talking about, this is neither maxima nor minima. So that is the concept. But if it is 0, 4ac minus b square is 0, then it can be either maxima, minima or undefined. So this is what we saw, but things cannot be smooth till we are not calculating, taking the example. So we'll take the example and then we will see.